Curves and irregular shapes make up a very large part of maths, since they pose great challenges to mathematicians. Different functions have their own unique properties, which make them all interesting in different ways, and are much more challenging than some regular shapes or lines. If we wanted to find the area of a perfect circle, we easily can using pi r squared. But for regular enclosed curves, it's much harder. If instead we wanted to find the gradient of a line, this is simple with the idea of the change in y over the change in x. But when we deal with curves, again we have to bring in more complex ideas. In the end though, these concepts are well studied and well covered, and we can thank Newton, Leibniz and many other mathematicians of the past for making the integrals and derivatives that are so often used today. But what I want to talk about is one of the more complex ideas that doesn't get the spotlight as much, and that's how we can find the length of a curve. It's not immediately obvious how we do this, but it's actually surprisingly similar to integrals and derivatives, and it all lies in infinitesimals. Let's start by quickly looking at how we create the derivative and the integral, since these ideas will be useful later. We'll start by having a point on the curve, a, f of a. We know that the gradient is given by the change in y over the change in x, but we'll need two coordinates to measure the change. This second coordinate will be at a distance h away from our first point, meaning its coordinates would be a plus h, f of a plus h. And we can then make an estimate for the gradient of the curve by finding the difference of their y coordinates over the difference of their x coordinates. The a's on the bottom cancel out, and so the difference between the two x values of the coordinates is simply h. This is a good start, as it looks like it makes a good estimation for the gradient, but we can still do better, since in between these 2 points, the curve has a slightly different gradient. So how can we go about making this approximation better? The best thing to do would be to bring the 2 points closer together, which we do by making h smaller and smaller until we make it infinitesimally small, and take the limit of the gradient as h approaches 0. This makes the gradient exactly the gradient of the curve at a given point, and all we need to do now is replace a with x, which is really just changing our variable and is purely notational. This probably looks familiar though, since this is our definition of the derivative. Next we'll derive the concept of the integral. We'll be deriving the Riemann integral, since this is the one we see the most, and it's the most conventional. The way it works is by estimating the area using rectangles. We'll just consider one rectangle for now to make things simpler. To find its area, we take 2 points like before, x and x plus h. The height of this rectangle is simply f of x, and like before, the width of this rectangle is h. We can say that this h is equal to b minus a over n, where n is the number of rectangles we use. This means the area of the rectangle is f of x times h. Finally, to find the area under the curve from -1 to 4 as before, we just use a sum of rectangles from I equals 1 to 11. In our example, we'd have x1 being -1, x2 being minus 0.5, and so on up to x11, which is 4. And when we take f of x of I, what we're doing is just finding the height of each rectangle at each x value. Just like before, we get a pretty good estimate, but we can easily do better by making h smaller. Now we take the limit as n approaches infinity, so that we use more rectangles and have less under and over estimations. Because h equals b minus a over n, this means that h also approaches 0, and it results in an almost perfect area between the curve and the x-axis. This is now the definition of the integral that we've all seen, but there's a slight ambiguity that I've not addressed here. As in most textbooks, you'll probably see a star over the f of x here, and that's because we've done a slightly simpler version of the integral, as normally we'd use partitions which don't necessarily have equal length, which would help us deal with slightly trickier functions, but since we don't need to deal with them, we'll use this more intuitive definition. Now we can actually start to come up with the formula for arc length, and we'll be using Pythagoras' theorem to do so. If we have these 2 points on a curve, we want to find the length between them, and the hypotenuse of this triangle is a very good approximation. We can find the length of the triangle by finding the change in x and y between the 2 points as we do here. Then the last length can be found by simply using Pythagoras. And in our example, this comes out to roughly 0.9. To be more general, we again call our first point x and the other x plus h, and so on. Again, h equals b minus a over n, with n being the number of lengths we'll take. The bottom length of the triangle we'd call x plus h minus x. The left length is f of x minus f of x plus h. Going back to the bottom length, we can see that the x's cancel out, and again we're just left with h. And the hypotenuse is the square root of the bottom length squared plus the left length squared. And just like before, we take the sum from 1 to n, or in our example, from 1 to 2. Just as a reminder, in our previous example that we were showing, we had x1 being 1.5 and x2 being 2. To make this more general, we change the 2 to an n, so that we can take more strips into consideration. This isn't a perfect approximation though, as the red line is still slightly different to the actual length of this section of the curve. So we'll take the limit as n approaches infinity, which also means that h approaches 0. With this, we can do some algebraic manipulation. We take a factor of h out of the second part of the expression, which ends up becoming h squared. This expression on the right has now simply become the definition of the derivative we derived earlier. We don't need to worry about our limits not lining up though, since we have h approaching 0, and because h equals b minus a over n, and n approaches infinity, we have h being incredibly small, and with the limit taken into account, 0. So we can rewrite this in a simpler form. Taking out the factor of h, it turns out we can also use our definition of the integral we came up with earlier to rewrite the whole expression. Our limits line up, our sums line up, we have a function of x of I, and we even have a h in there. So we finally have our expression for arc length. Before we finish, I want to run through an example, so if you don't want to go through some regular integration, you should probably stop watching now. Let's say that we wanted to find the length of the curve y equals e to the minus x from 0 to 1. Before we start, we'll get a lower bound to make sure that our formula doesn't have any errors in it. We know that the length of the white curve, which is what we're trying to find, must be greater than the length of the yellow line, since the yellow line is the shortest possible distance between the 2 points. Using Pythagoras, we can find that L must be greater than roughly 1.183. To find the actual length of the curve, we'll use the formula that we've derived. We can simply put our bounds in place, and since our curve is y equals e to the minus x, the derivative f prime of x is minus e to the minus x as a standard result. And because we're squaring it, we have minus e to the minus 2x, which we can substitute in. Now all we have to do is solve this integral. I won't go into too much detail, but I'll go over the main ideas. We start with a u substitution of 1 plus e to the minus 2x, giving us that du equals minus 2e to the minus 2x. This may seem to cause problems at first, but we can actually get e to the minus 2x in terms of u, and rewrite dx with respect to u, which is perfect. Substituting this in, we end up with a nicer looking integral. However, we still need to express our dx in terms of du and change our bounds. We'll rearrange this expression of du in terms of dx, and then substitute the dx into our integral. We'll also simply take this factor of minus a half outside of the integral. Next, we'll use our original u substitution to change our bounds, by letting x equal 0 and 1. We'll move these new bounds to the top right hand corner to avoid things from looking too clunky. We'll swap the limits by using this minus sign, and now we can move on to the next step. Here we have to use another substitution of v equals the square root of u, or u equals v squared. We can get that du equals 2v dv, and we can then once more change our limits, expression, and du. We can use long division here to express this as 1 plus 1 over v squared minus 1, and then using partial fractions, we can get this into a form which we can directly integrate. This leaves us with a v minus some natural logarithms, which after substituting the bounds in, leaves us with roughly 1.19, which lines up with our lower bound from before.